Number one. Number one. Can somebody read that to me? What is it saying to do? Evaluate. Thank you. That's a good word.
From 2 to 6, find the area of 1/2.
Okay, that's what we're doing, but what's the calculus words? We are taking the integral of 1/2 x in respect to x, that's what the dx means, in respect to x, from the lower bound 2 to the upper bound 6, right? Okay, so to get a good grasp of these, you've got to be able to graph. So we're looking from 2 to 6, and we're looking at the line 1/2 x. What's the y-intercept? 0. And it's got a slope of 1/2, so it's just going to do something like this, right? And we're looking at the region from, let's say this is 1 and this is 2, 3, 4, 5, 6, whatever that is. We're looking at the region that's bounded from 2 to 6. So we're looking for this area. We don't care about this area anymore. You guys okay with that? Okay. We're not approximating. We're finding the exact area. So do you know how to find the area of that shape? It's a what? It's a trapezoid. You could cut it into a rectangle and a triangle, and that's fine if you do for now, but later on you have to know the formula for the trapezoid because we are going to do trapezoidal approximations in the same way we did rectangular approximations. So you need the area of a trapezoid.
Like cut it into trapezoid?
Right. So it's a good practice to know the area of a trapezoid. What is the area of a trapezoid? One-half b1 plus b2 times height. Okay. Now, this trapezoid is laying on its end. The bases are what? The trapezoid always has, what does bases mean in a trapezoid? They're parallel. So normally we see the trapezoid like this. We're stacking it on its end. The height is what? The distance between the two parallel bases, right? So what is the distance between the two parallel bases? 4, because we subtract the 6 minus 2, right? So 4. Now, we've got to figure out what B1 and B2 are. How do I figure those out? I got to figure out that height, and I do that by plugging in 2 to the equation, right? So we'll say, I'll just show it here. 1/2 times 2 is 1, so we know this is 1. I know that's elementary, but you know. And this point is 1/2 times 6, which is 3. So we know this length here is 1, this length here is 3, this length is 4. We don't care about the diagonal. So we have 1 plus 3 for our bases. So we got 1/2 of 4 times 4, which is 8. So we can say the integral from 2 to 6 of 1/2 x dx equals 8. You guys okay with that? All right. Number 2. We want a function so that when I do a right Riemann sum, a right-hand rectangular approximation, we get an overestimate. So we want to have a curve, and you can just experiment, but either way, you wrote it down. What determines whether it's an over or under approximation? Whether a function's increasing or decreasing, right? So I'm just going to quickly do this. There's, let's see, there's an increasing function. There's a decreasing function. Concavity has nothing to do with it. So if this is increasing and I do a right Riemann sum, let's just cut it into 2 rectangles. Am I going to start here and go that way, or am I going to start here and go that way? I'm going to the right, from the right to the left. From the right to the left. That's a right Riemann sum, right? On this one, if I'm going a right Riemann sum, do I start from the left and go to the right, or do I start from the right and go to the left? So that and that. So what makes a right Riemann sum an overestimate? Increasing. So my answer will be any function that is strictly increasing. Are we good with that? Okay.